Good afternoon, everyone. My name is Jong-Young Lee. So I'm very glad to participate the 11th IEEE Symposium on Computer Application and Industrial Electronics. So I will present the topics on nonlinear disturbance estimator-based control for nth-order system with matches and mismatches uncertainties. So I'm gonna talk to you guys the problem and a preliminary first. So this is a proposed to consider an order single input and single output nonlinear system with the matches and mismatches uncertainties. So you can take a look in this formula. In this formula, this is the system nonlinear input and a single input and single output nonlinear system, CISO system. The control objective is to construct an algorithm in such a way that the response x1 convert to desired state x1d with a minor error in the appearance of unknown non-zero mismatches, unmatches, and matches disturbance uncertainties. So I'm gonna talk to you guys the main results. First, the sliding manifold and controller design. A series of, in order to control the CISO system, we propose a series of sliding manifold like this formula. Like this formula, you can take a look in this one. So where delta Zi represents present tracking error. So it can be seen that if the sliding manifold Si is equal to 0, it means that Xi is converted to 0. It means that sigma I is also go to 0. When sigma I is also go to 0, it means that delta Zi is also go to 0. Delta Zi is go to 0, it means that Zi is go to the ZID, go to the desired state. So we can take derivative of the sliding manifold, so we can get this formula. So it's very easy. We do some mathematics, we do some math, so we can get the xi dot. So this step I equal 1. The tracking error of the channel first is computed by this one. So where delta Z1 is the tracking error of the channel 1 is equal Z1 minus Z1D. So we can take derivative of this one. We can get this formula, this equation. So from the previous equation, xi dot, so we can get the x1 dot, follow this formula. So we do some math. So with the d1 bar is equal this formula. Less d1 bar hat is an approximation of d1 bar, and desired state z to d is chosen by this equation. So we can substitute z to d to z to d in this the equation, so we can get x1d is a very simple one. So the step I equal to is mean that we calculate the tracking error. We consider the channel 2 with the tracking error is delta z2 equal z2 minus z2d, where z2d is a desired state, a virtual desired state. So we can take derivative of delta z2. So we have this formula where this one we can get. So you can take z2d equal this expression. So if z2d does, we can take derivative of this one, and we substitute to this equation. Substitute to this equation, we have this formula. And finally, we can get the x2 dot, where d2 bar equal this formula, Of course, we do some math before we can get to D2 bar. So let D2 bar hat be an approximate of D2 bar and the desired state. The 3D is chosen by this formula, and finally we can get x2 dot equal this one. It's very simple because we can substitute the 3D to this equation, so we can get this one. So it's entirely similar. The step constructing the sliding manifold for channel I's are entirely similar to the designing process of channel first and channel two. Thus, the following expression is achieved. So you can take a look. We have xi dot equal this formula, and where di bar here, we can get this formula, and zi plus 1d, this is a desired state. This is a virtual desired state of channel I. And we have also di bar tilde equal this one. And finally, we can calculate. We can consider the step I equal n. The sliding manifold is computed as follow. X n dot equal this expression. Where z n dot equal this formula. Where this formula come from? So we can get, we can go back to some previous slide. We have this one, z and dots equal this one, and we replace d and zt by z and dt by this one, by this formula, and finally, and also we can get the z and d dot. Z and D dot is equal this one, equal this formula. This is a Z and D. Z and D is come from here. Z and D come from here with I is equal n minus 1. We have this formula. And finally, we substitute two formula Zn and Z dot n and Z dot nd go to this formula. Finally, we can get xn dot. Xn dot is to follow this equation. So we can choose the controller from this one, from this sliding manifold. So we can choose the controller U equal this equation, where Kn and Ks is a lesser than 0. Kn and Ks here is a lesser than 0. It's positive value. Continue. I'm going to talk to you guys a nonlinear disturbance estimator. The abbreviate NDE. NDE is abbreviation of nonlinear disturbance estimator. So with the step I is equal 1 to n minus 1, the nonlinear disturbance estimator is proposed as follow this formula, as follow this equation. Where PI1 and PI2, PI1 here and PI2 are the existence state, and DI bar hat and DI bar dot hat denote the estimate of DI bar and DI bar hat respectively. And also QI1 and QI2 and phi I here are the constant, a positive value. Positive constant, so we can give this value. The approximation error are obtained by this one, by this formula. So from this equation and two equation here, we can do some math. Finally, we can get this equation. And continue, we consider the step I equal n. The nonlinear disturbance estimator is represented by this equation, with the tracking error is di bar tilde is equal di bar minus di bar hat, and also di bar dot tilde is equal di bar hat, di bar dot minus di bar dot hat. Then finally, we can get, we do some math in this one. And in the slide 7, we also have this equation, because we take a derivative of this one. We also use xn derivative. We can take this one, this equation from slide 7, and here we take xn dot from here. And finally, we have this equation. And let's recall phi and e tilde are the vector of the total disturbances and its estimated error respectively, given by the following expression. We have phi is equal this vector, and e tilde also this vector also. So let's assume that the vector of total disturbances satisfy the following condition. Following this condition, so we have the magnitude of derivative zeta of phi is smaller than alpha, where z is equal 1 and 2. This is derivative of first and second time, and alpha is positive value also, so we can give this form, this value. But normally, alpha as we do not need to before. We just know that the positive value. That's all. The dynamic system of the nonlinear disturbance estimator is formulated by this equation. So how do we have this formula? So we can go back some previous slide. At this slide, we have di bar tilde dot and di bar dot tilde and dot, so equal this equation, and this one is also have equation. And finally, and we also combine with this equation, we have the e tilde dot equal this one dot and dot here, and finally we have the error tilde dot equal 8, the error tilde plus b phi dot plus e phi 2 dot. So whereas the a where the metric A, metric B, and metric E is follow this formula, where A is a 2n by 2n matrix, B and E 2n by n matrix, and its value is follow this expression. So continue, I'm going to talk to you guys about the stability analysis. So because in this subject, we propose many equations, many mathematics equations. So that's why now we talk to you guys about stability analysis. The overall stability of the CISO system using nonlinear disturbance estimator and the robust controller is proven in this section. So it's constantly a paper to choose the proper coefficient of QI1, QI2, and phi I equal 1 to n, such that the eigenvalue lambda I representing the eigenvalue of metric A's are places on the left of the complex plane. So thus, there S is positive symmetric matrix B and M, such that this equation ATP plus PA equal minus M, and less lambda max M and lambda min M are the maximum and the minimum eigenvalue of the matrix M. So we always have this inequality. We always have this inequality. So the first one, we consider the conversion of the nonlinear disturbance estimators go to zero. We consider the Leonov function VE tilde is equal E tilde T multiplied B multiplied E tilde. So we take the derivative. We have this formula, and from the final inequality, so we can take a look the magnitude of the error tilde is bounded by the gamma, where the gamma is equal to this one. Gamma from here, from this equation, from this expression, so we can calculate the gamma is equal to alpha multiply this equation. So therefore, the function d1 bar tilde, d2 bar tilde to dn bar tilde is bounded by also bounded by gamma. So because you can take a look, this one is bounded by gamma is mean that x of element here is also bounded by gamma, also bounded by gamma. So um, uh, continuously, I will talk to you guys the conversion of sliding manifold. Sliding manifold xi is also equal to zero. Let's consider the candidate of Leonov function Vn Sn is equal to this one, and we take derivative. We take this equation where we have xn dot equal this formula. So we look back some previous slide. We have xn equal this formula, and we choose the controller here. We can replace the controller to this equation, and finally we can get this the expression, and finally we have this one, and we can get the final inequality. Therefore, sliding manifold as n will fly to small neighborhood of zero, is given by xn will smaller than gamma minus ks over kn, whereas gamma is larger and equal or equal than ks. Therefore, the tracking error delta zn also decayed to a small neighborhood of zero. So it's a very similarly, the stability analysis performance with other channel of the CISO system. We can take a look at this formula, and therefore sliding manifold Si is already K to a small region bounded by this one. It's very similar to this one. And finally, I will talk to you guys. I'm gonna talk to you guys simulation and discussion. So we consider the system here. We consider this a system with the simulation scenario where t is larger than 0 and smaller than 0.5 second. We have the disturbance like d1 and d2, like this equation. When t is larger than 0.5 second, so we can get so we have the disturbance like this equation d1 and d2 equal this formula. So there are some parameter we need to give for the controller and the nonlinear disturbance estimator, and the desired state is equal 1 plus psi of 3 to 5 pi t. So this is the simulation result. So you can take a look here. In this simulation results, we compare with the other methods. We compare with the other methods. So you can take a look. Our methods is always better than other one. Uh, the red, the red, uh, the red line, the red dot line, the red line is a proposed method. This one is a proposed method. The rest one is a proposed method. You can take a look. The rest one is always close track the reference one. Why is the other methods is not like that? And so it's not same. It's not exactly the error is also lesser than our methods. This is a tracking performance Z1. And so you can take a look at the performance of nonlinear disturbance estimator of the two bar hat. So you can take a look at this one. The estimation one is a very close to track the real one. Very close to track the real one. This is a channel 1, channel 2. So you can take a look. And this is a sliding surface, sliding manifold of X1 is convert to 0, And sliding manifold of X2 is also convert to 0. And this is the controller without the chattering effects. So you can take a look. I have already talked to you guys about our conference paper and our research. So if you have any questions, so let's give us. Thank you.